So today I'm going to give you an overview of PATRAN Nastran, the application part of it, focused on aircraft structures. I'm going to take you through my slides. So first one is FEM, FEA. Probably you might have aware of why we are using FEM and FEA, why we're not the closed form or closed loop solution methods such as mechanics of materials or strength of materials. Well, if you look at the closed loop solution methods such as mechanics of materials or strength of materials, they all use the simplified assumptions for the simplified geometries. They work out well for the simplified geometries and not for the complex geometries. They are primarily for they 1D. They simplify the geometry into a 1D assumption, and then they use the standard procedures to find the solution. Whereas moving to theory of elasticity primarily deals with 2 dimensions. And then coming to FEA, where we have the luxury of analyzing complex geometries with various boundary conditions and various loadings. Mainly FEA is used for the 3-dimensional geometry problems, 3-dimensional geometries. Some of the pioneers in this field is Zinkovich, Clow, and a few others who had developed this FEA. And this was back in the year 1950 and 1960s, where they come up with this FEA methodology, and then it was coded, and then finally you can see a lot of commercial packages coming out. Eventually by 1980s or around 2000 something, a lot of commercial FE packages came out with various different functionalities and those kind of stuff. So if you look at the finite element methods, basically it is an approximate method. It's a numerical method where we break the continuous, where we break the domain into smaller smaller domains, where we break the bigger domains into smaller domains called elements, and those are all assembled in a matrix form, and these elements are interconnected at the nodal points, and we solve the compatibility conditions, which is strain displacement relations and those kind of stuff at these nodal points. From the constitutive relationship, which is primarily our Hooke's law, you find the stresses and strains develop at these nodal points, and you can average it over the elements as well. I'm sorry, these elements, which are this complex geometries, which are broken down into these smaller elements, which are assembled in a global stiffness matrix. And then we solve this equation over here, which is K is the stiffness, U is the displacement, and F is the forces acting on those elements. And then once the displacements have been found, then using the constitutive relationship, we can work out the stresses and strains. This is the basic idea of FEM and FEA in general. So just moving on to the next slide. So I have pretty much summarized in the last slide why we are using. So we are using it for the complex geometries, and again 3D geometry. On the right hand side, you can see that I have put how a real structure, a rocket or an aircraft, which is broken down into smaller elements. And then there are various different finite element commercial packages available. The primary focus on this is of PATRAN Nastran. And then we work out the displacements, and then you can post-process the results. What do you mean is you can import the results once the analysis have been run. You can import the results into the system and then see what is your critical areas and what is the your maximum displacement regions, or what are the maximum stresses developed, or if the stresses developed are within your allowables or not, and those kind of stuff. One downside of the finite element analysis is the system time, processing time. If the model is bigger the model, the bigger the processing time, bigger the machine time, and the number of elements. And one thing the user has to be aware of it is like how to properly use what elements needs to be properly used in idealizing the real structure into the discretized model. How you can bring out the exact behavior of the real structure of the into the finite element. It's basically the mathematical model one has to be aware of. It's basically the physics involved. One has to understand the complete physics, how you can bring out the exact physics into the model. Suppose you are to give you example, like suppose you are analyzing a plate with a hole. Suppose imagine there is a panel in the aircraft, because it might be a panel in the aircraft or a panel in a car body where you have a bolt or something. So you remove that, and then as if there is a dent or hole in the panel. So you have to analyze what is the stresses developing. You have to know what kind of elements you are using, and what kind of how many number of elements you are using, and how they mesh, and how finally you could mesh, so that you can bring out the exact behavior and what kind of properties you need to use. User. So we are going to talk those things later in the course, later in this module. So I'll be moving to the next slide. Coming to Patran and Nastran, there are a few things that we need to understand. So first of all, this one, there are few other FE commercial packages available in the market, such as ANSYS, Abacus, FEMAP, and those kind of stuff. And Patran and Nastran, these ones are primarily for the aircraft industry. This was developed in the year 1965. This was back when the founder McNeil Spindler, who developed these codings for NASA. He was an aerospace engineer, and he developed this Patran and Nastran just for his application on NASA to execute his projects, to carry out the projects for NASA. And later on, the company, it occurred to various different small industries, and then the coding took a different turn. And later on, it started with the Nastran, and then they developed Mark, and then the latest one is Apex, which came out a couple of years back. So this is a very brief of Patran and Nastran. So moving to the next slide, I'm going to take you through the structure of Patran and Nastran. This Patran and Nastran, as few of you might be wondering, why Patran and Nastran? Why not ANSYS? Why not other things? Because Patran and Nastran have been exclusively developed for aerospace industries, and it's been used in a wider number of industries, like primary structures, secondary structures, and helicopter structures within the aerospace domain. And it's extremely organized. One of the organized softwares I have come across. This Patran and Nastran, it's Patran is the pre and post processor, and Nastran is the solver. If you look at the organization of the Nastran file input, there are different sections that within the Nastran. Nastran is the solver. Again, I remind you, this Nastran is like it's separated into different sections, such as Nastran's statement, file management section. As you can see on the screen, like executive control section, case control, and bulk data section. Probably you might be wondering, what are all these? These are when I probably I can jump back and forth. I can, on the next slide, you can see a simple frame, which is, we are modeling a simple frame with a point load. Here, if you see on the right hand side of this model, you can see how it's like a coding where you could see that the first line you can see ID trust sample. On the second line you could see SOL. So SOL stands for the solution. Solution 101 is the linear static analysis done. So if you look at the structure, I'm just showing you an example just for you to understand that this is an extremely organized way of running the FE program, where you have the standard formats and standard load cards and material cards and all the constraint cards listed down in a very standard way of thing. On the executive, case control, and bulk data sections, these are the different types of sections which are needed for the analysis to be run, which are basically the information of the grid points, which are the nodal points, loads, material, and these, and the force cards. Going back to the previous slide, you can now see that the different sections, whatever I have been mentioning in the example which I have shown you, that these have been arranged in a very organized manner. So this allows the user to edit the database file directly on the notepad, and then this gives you flexibility to to run the Excel macro or something if somebody wants to run the Excel macro and then do the manipulation without even interacting with the preprocessor. This gives an opportunity to do that. Moving to the elements which are commonly used in Nastran and Patran, we have different types of elements, which are 0D, 1D, 2D, and 3D elements. These are various different elements we have been using in Nastran and Patran, which are available for the commercial use. And the library contains over about 50 elements, axis and two-dimensional elements. Moving to the slide back, I would like to tell you that the one thing which I liked about the Nastran and usage of Nastran and Patran is, like as I mentioned, it gives a bit of flexibility. If there is a change in the material, or if you want to change the material, if you want to change the load, or if you want to change any of the stuff or the boundary conditions, you can directly go onto the notepad, directly open the input file, which is a standard set of coding, and directly manipulate the file, directly amend the file, and then just solve it using the solver. So in that way, Nastran and Patran is very flexible, highly flexible. In this slide, I have shown you the input file, which is dat file. This is the dat file. Once the model is modeled in Patran, which is the preprocessor, and then once you save it, it generates a type of file called DAT file, dat file. When you open, I have given you an example below. I have shown an example below. When you just open it, it gives a set of cards, which is called Nastran cards, which has the complete information of your model in terms of boundary conditions, in terms of forces, material cards. All those things come into, have been written into the data file. So this gives you a complete freedom for the user to, edit and then amend whatever you wish, and then run it. Once the data file is solved using Nastran, once you run the analysis using the solver, which is Nastran, it generates two types of files. One is F06 and OP2 or XDB. One is F06. F06 on the right hand side, you could see where I move the cursor, you could see the snapshot from the F06 file, where I have put the resultant of the forces at the constraint points. As you know that FEM is primarily based on the displacement method, where we solve the static boundary conditions, where we meet the static conditions like compatibility conditions, sigma f equal to 0 and sigma m equal to 0. So you can see this on the F06. Primarily, Nastran prints all the force resultants or the boundary conditions and the elemental forces and everything. This is also, again, it's readable with any notepad, wordpad. So if somebody wants to directly write a macro or something that could import the result directly into the Excel file or dump it into the Excel file, it gives the user flexibility to do it. And the another type of file which is generated is the OP2 file, which is mainly for the post processing. There are two types of files, which are XDB and OP2, which is mainly used for post processing. If somebody wants to post process the results into the Patran, again, they can import the results into the Patran. Just take the displacement plots, stress plots. So moving to the next slide, I have shown some snapshots from PATRAN Nastran. On the top left corner, I have shown a wing model where you can see the finite element model itself and then the results. So this is just a snapshot from PATRAN Nastran. This is again on the right hand side. This is again on the MSc Corporation, where they have developed different packages for different things. One is PATRAN Nastran, Mark, Ditron, and Fatigue. Nastran has a different solution capabilities: linear static, non-linear static, fatigue analysis, dynamics. But still, they have developed for fatigue. They have developed MSc Fatigue, which is exclusively for fatigue, and Ditron for dynamics, and Mark is again for implicit dynamics, and Adams is multi-body dynamics. Moving to the last slide, as I mentioned earlier, there are various different commercial packages available in the market, such as Hypermesh, ANSYS, Abacus, and FEMAP. But this PATRAN Nastran is extremely an organized software, which gives the user complete flexibility in editing the model without even opening up the pre-processor and post-processor. And it's primarily focused on the arrow structures. Some of the opportunities a structural FE engineer would have is an FE engineer and an FE analyst within the aerospace industry. And the other possible opportunities are like stress engineer and the structural engineer. If you look at the organizations that have been that are using this PATRAN Nastran, various different government organizations such as DRDO, NAL, HAL, CAMPS, Center for Urban Systems, and ISRO, they use PATRAN Nastran for the satellite structures. And some of the private major players are Airbus, Boeing, Bombardier, Embraer. These are all the private major players, and various different consultancies that have been using this PATRAN Nastran for analysis of the primary structures, secondary structures, and landing gears. Just to go back and to summarize it. First of all, FEM, we are using it for the complex geometries and mostly 3D geometries, because it gives the opportunity for us to use it for various different boundary conditions, various different materials, loadings, and a convenient way of analyzing this to complex geometries. Moving to PATRAN Nastran. PATRAN Nastran is mainly used by the aircraft industries worldwide. PATRAN is the pre and post processor. Nastran is the solver. So it generates 3 types of files. PATRAN, once you model the geometry in the PATRAN, and once you run it, it generates dat file, which is the input file for the solver. And once the analysis is submitted, and once it is solved by the solver Nastran generates 2 types of files, which is F06 and OP2 file. F06 is the mainly results, elemental results, which is stress, elemental forces, elemental stresses, displacements, and OP2 is the file which is used for post-processing. So one of the things on the PATRAN Nastran is it gives a complete flexibility. You can directly, using the notepad or wattpad, you can directly edit the input file. If you know the cards, you can directly compile yourself and directly run it, solve it. And F06 file, once the Nastran generates the F06 file, you can directly use any Excel macro or just copy and paste the results into the Excel file if you want to do further calculations. So these are some of the commonly used Nastran elements that have been used within the PATRAN Nastran. And moving to this slide, just to give you a recap, this is a sample model of the frame that have been analyzed under a point load. On the right hand side, you can see the equivalent Nastran cards on the Nastran input file that have been generated. This gives you this will give you a brief overview of how it has been organized. First one is like, there are different sections, as I mentioned earlier, there are different sections of the Nastran input file, which is Nastran statement, file management system, executive control section, case control and bulk data section. Probably you may not be seeing these 2 ones, because these 2 ones deals with the computer buffer memory and those kind of stuff. And what is over here is starts from the executive control section. Over here, it gives the solution type that you are requesting. And then the case control is nothing but the load case. What is the load case? What is the static load that have been applied, and what kind of boundary condition? And if you look at here, over here, you can see load equal to 10, and this 10 nothing but the load ID is 10. If you look down, the load ID 10 refers to the point force, which is of 1000 magnitude. So in that way, you could trace back what is what. And as far as I have seen, this PATRAN Nastran are extremely organized and extremely user friendly. Thanks for joining.